my quaternions, strict in my matrices. Before we get started, you establish an order. Geometry, column, and row sorted. 16 by 16 matrices allotted around the diagonals where you'll find my identity. 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Will the axis turn and look at me? I no longer see an RGB. The first step in a rigid body physics is broad-based collision detection. Axis aligned bounding boxes, reducing the load on future point reduction. Once you got collision pairs, compare geometry with the back of your mind. You need the closest point so there's no irregularity within the results you find. You want a piece of me? You best dodge my motion tween. I'm in the only place left that you've never seen, staring at you from behind the computer screen. It's like freshman year class of Mr. Peabreen. Once you define your geometric space, likely one of a Minkowski order, you can sit back, crack your knuckles, it's just what the doctor ordered. Remember what I said about rows and columns? Well, now you gotta do it again. As objects collide, they become part of a tree. Each origin of a triangle has their own world translation matrices. Many collisions happen simultaneously, but it's all imaginary. We're not concerned with the constant speed of light, c. Instead, we look at the problem through the lens of linear programming. But even that nomenclature is not as obvious as it seems, for that area of study really means a mathematical method for determining the best outcome. It's a quest for optimality, not some linear algebra formality. First you check for geometric penetration, then you determine the angle of incidence based on the object's extents and normals, rotated in every possible axis, throwing up bows as far as the reach in each direction, until you've assembled an array of each collision in the list. Then you take that list and reduce the redundancies. There's only so many ways two triangles can be penetrated, and there's an easy way to represent it. You just have to use barycentric coordinates, pass them into your constraint solver. Next thing you know, you're correcting penetration for the next time step. What some of us like to call delta time or DT. That's a place where you'll find me. It's in the place between two T's, possibly T1 and T2, if you want it simply. Problem in solving the interpenetration of geometry is that you can't possibly compute every point in time, at least not for high-speed performance simulation. So you have to do some simplification and make DT proportional to your rendering intervals, as most graphic cards of today are multiples of 33 megahertz, 30, 60, and 90 frames per second. Simulating each step at that rate can smoke up a lot of CPU Buddha. Some try to parallelize it with CUDA, Compute Unified Device Architecture made by NVIDIA, or you can try to use open source models like OpenCL on any modern Intel processor. Any one of these techniques, if used properly, can significantly increase your speed, but a warning you must heed: if you compute forces in parallel instead of sequentially, you'll have to average out the changes in inertia, or your model will become unstable and jerk ya. That in itself can be a challenge, since computing each iteration in parallel can be difficult. On top of that, you have to be sensitive to damping values, precision errors like those encountered while converting 64-bit floats to 32. You have to keep track of restitution, which is the net force when two contact manifolds produce a collision. Will it stick or bounce is basically what it boils down to. Okay, and maybe in what direction, but it's a relativistic transformation, baby. What have colliding polygons done for you lately? Well, just about every video game, any particle explosions, or fuck even biomedical animation, flight simulation, and automated vehicle navigation. Okay, so you've reduced your trees by using simplices. Maybe a Gilbert Johnson Curtsy, of course from Oxford University, or some other methodology. Filter lists down now, there's basically one thing left to do: integrate the values, integrate the forces, if you will. But this is the easy part. For each contact manifold, you take its points, find the distance from which it is separated from each object's origin, and use that point to apply linear or rotational velocity. Then you apply its transformation matrix, or quaternion if that's the way it be. And that's where you multiply the transformation by the change in time, delta fucking T. I'm out of here like Pythagoras. My A squared plus my B squared is equal to I'm the fuck out of here. But if you want to see my C squared, you better double down or double dare, cause Dr. Sistray is going off the air.